of big data, and also we have discussed the various components of Hadoop ecosystem. All right. So before we start further, do you have any questions? The agenda for today is to first go over the various components of Hadoop, and then go over the general ecosystem, just the CloudX Lab part. And afterwards, we will start with HDFS. Then we will talk about one of the very big component of Hadoop called yarn, yet another resource manager. And afterwards, we will talk about, after yarn, we will talk about MapReduce. And then there will be three sessions, one basic session on MapReduce, and then three sessions on the advanced MapReduce. Afterwards, we will proceed to Pig and Hive. All right. Let me just write down whatever we have talked so far. Okay. All right. So this should be clear to everyone. So first, we will again do a recap, and then we will go with overview of CloudX Lab so that all of you are aware of the how to access the ecosystem, and then HDFS, and then yarn, and then MapReduce. But today's agenda most likely be up to here. Okay, these three topics is what we are going to cover today. All right, great. So do you have any questions before we start? All right, yes, Prem, you have a question for me? Okay, just a second. All right. So let's start with. So do you have any questions, Prem, Ella, Sumai, Amrutan, and Ritika, Ashwini, Ravi, Liu Song, Stanley, Kulbir, Katie, Lokesh, Lakshmi, Lee, Abru, Sasti, Yogesh, Magini, Mahesh, Alan. Do you have any questions for me? All right. All right. So, okay. Okay. So, let me just do a quick recap. So, first thing we discussed was the big data part. So, in these classes, which we are going to have further, like 12 more classes, we are going to go with the definition of big data as any data for which for to handle the kind of data we require distributed computing, we will call it big data. All right. So that's the strict definition we are going to follow during these sessions. Any component we are going to discuss in these sessions is going to be related to distributed computing. All of the components, all of the components that you see in this screen are distributed in nature. What does it mean by distributed? A program that runs on multiple computers to accomplish a single task. Okay, or you can say that we are using multiple computers in order to accomplish single task. All right, so here we are. The main component in Hadoop ecosystem for big data processing, basically these are the main component, and the these are the components of the Hadoop ecosystem. And the main component of Hadoop ecosystem is Hadoop distributed file system. The way in your computer you have a disk and you have a file system, and that's where everybody stores its data, whether it's Windows, whether it's databases, whether it's your settings, whether it's your files, all of these things go into file system, right? Similarly, in Hadoop ecosystem, almost everything goes into Hadoop distributed file system. Whether it's the output of MapReduce jobs, whether it's the log of MapReduce jobs, or it's the input to MapReduce jobs. Similarly, the data that is actually physically stored by HBase. So I'll describe what is HBase. HBase is like a database. So almost everybody in the ecosystem of Hadoop stores the data in Hadoop distributed file system. And what is so special about this file system? It hides the complexity of storing huge data on many computers. Or in another words, you can say Hadoop distributed file system runs on many computers without any uh, without any inputs from the users. Okay, for the user it's just a file system. As I will show you, the Hadoop distributed file system will look like a normal file system, like the way you have C colon and there are folders and there are files in those folders. Exactly in the same way Hadoop distributed file system exists. Okay, next is, on top of Hadoop distributed file system, you have something called Yarn. Yarn is yet another resource negotiator. Okay, what does Yarn do? Yarn basically runs a program on many computers simultaneously and make sure that the program runs closer to the data. Okay, we'll go into the architecture of Yarn. And then you have, now talking to Yarn is like talking to operating system, right? But as a user, you would not like to interact on that level. And therefore, there are little higher level tools like MapReduce, where you write your program in two functions. One is called map and other is called reduce. And these two functions get executed by Yarn on the Hadoop cluster. Okay, and so MapReduce calls Yarn, and Yarn does the work by executing program near the data, and the output is stored in Hadoop distributed file system. Now, then what's the use of HBase? HBase is another files kind of a storage for you. So HBase lets you store data in the form of records. Okay, so what HBase is to the file system is similar to what HBase is to HDFS is similar to, say, MySQL is to the local file system. Okay, so the way in a local file system, in a file, when you are storing data into file, it's not efficient to store data in file where you are modifying various lines from time to time. because when you change a line in a file, everything the whole file is rewritten. In the same way, in HDFS, the whole file is rewritten if you try to modify anything. Okay, so HDFS is great for append only kind of use cases where your data is just being appended. But if your data is continuously being modified, HDFS is not great. In those cases, you better choose a database kind of scheme which lets you talk in terms of rows and columns. And that's what is HBase. All right. So we talked about HDFS, Yarn, MapReduce, HBase. And the other way to talk to Yarn is Spark. We will also talk about Spark in one of the sessions for 3 hours. And we will run a couple of examples on Spark. Okay. One, we will run the Spark streaming, and other we will run the normal word count problem on Spark. Yes, Prem, are you not able to hear? All right. Do you have any questions for me as of now? Okay, looks like no questions so far. Okay, so after HBase you have Hive. Using Hive, instead of writing Java code or instead of writing any code in MapReduce, you use Hive. So whatever query you write in Hive, that gets translated internally into MapReduce and then Yarn. So you write your query as a SQL, and that query gets internally translated into maps and reduces, and that maps and reduces get executed on Yarn, and then the output is saved into distributed file system and then given back to you. So the whole cycle goes like this: from Hive to MapReduce to Yarn to HDFS and back to the user. Okay, and then similar to SQL, some people realize that they require a little bit more granularity and control, because the SQL, the structured query language which we study in databases, that query language is not great when it comes to distributed computing. And that's where the Pig Latin came into play. Pig Latin looks like SQL, just that Pig Latin lets you do one step at a time. Okay, so it's a kind of a data flow language, while in Hive you execute the whole query. So Pig Latin is very similar to Hive, as you will see further. Okay, so Pig Latin gets translated into MapReduce and then Yarn and then back to the user. And then you have something called Mahat. What is Mahat? It's basically a collection of algorithms for machine learning and other analysis. And we will go through one example on Mahat in upcoming sessions. All right. And in a typical scenarios, before you start processing, you need to bring the data, right? Bring the data to your Hadoop environment. So there are these two very popular tools. One is called Scoop, okay, and other is called Flume. These two tools let you pull the data from external world into Hadoop and back. So using Scoop, you can execute a command of Scoop that will bring data from structured sources such as a database. Typically, it's a database, and you can pull the data from that database into either the file system, HBase, or Hive. Okay, so you can pull the data from any of those sources into Hadoop, and once you are done with your analysis, you can push back the result from HDFS to your usual database server. Okay, so that's the job of Scoop. That's the job of Scoop. bringing data from the structured source such as MySQL or a relational database to Hadoop. When we say Hadoop, it means Hadoop file system and HBase and Hive. Okay, and once you are done, you can take the data from any of these sources back to the database, the structured database. Next is Flume. What does Flume do when Scoop can do almost everything? So Flume does very interesting work. It basically pumps data continuously. Continuously is the keyword here. So Flume keeps running continuously on all the machines and pushing data to HDFS parallelly from all of your servers. Okay, so for unstructured sources, if you want a continuous pump in of the data, as and when data, it pushes data to HDFS as and when it comes. So we will go through the hands-on exercises on Flume and Scoop as well. Okay, so these are the various important component, and there'll be Zookeeper as well, to which we will devote around 2 hours. Okay, that is something not mentioned here. We'll mention it later. Also, when in a typical environment, or in a typical what do you say, in a typical project where you have to get certain results, let's say you have to build a recommendation engine. The most typical, most common use case of big data stack is generally getting some kind of insight, some kind of recommendations, some kind of um, analysis. So in those typical cases, uh, there are many components involved. It's not only one. Let me give you a couple of examples. Say for example, you are building a recommendation engine. Your data first would come from the structured sources, and then, okay, your data would come from your structured sources. Let me draw, that'll be nice. Okay, okay, let me just draw it. All right, so this is a typical I'm going to draw a little bit over it. So let's say you have got web servers from which data will come to your HDFS, and that's your first step, say. And then afterwards you will be doing the cleaning using maybe piglatin. Okay, using piglatin, that same data what you have pulled using Flume into HDFS, you are running piglatin to clean it up. And then the next step is to maybe run more queries on top of it. Maybe some data analysts have given you some SQL to generate some more clean data. And so it's a combination of 1, 2, and 3. And afterwards, when you have like 3 column data of very clean data saying this user likes this product this much, okay, and afterwards you may want to run it through Mahat. Okay, so a recommendation is generally, a recommendation engine means that you want to give recommendation to users, and typically what you do is you pull out the log from web server, because website is the place where your users are interacting with you. So from those logs you figure out the behavior of users, meaning what does your users like and what does your users use, and based on that you do the analysis using pig and hive and figure out the ratings of individual product with respect to each user. Okay, so generally you don't have luxury of collecting the ratings of product from the users. Instead you try to analyze that this user has visited this page so many times, and therefore this user might like this product this much. Okay, and once you have figured out that, then you can start giving them recommendation using Mahat. Okay, and once you are done with giving recommendation using Mahat, then you might like to use Scoop. You might like to use Scoop to take data from Hadoop back to your web server. I mean, the database of your web server, and then goes to the user. Okay, so this is a typical case scenario. Okay, looks like I have missed so many questions. For some reason, it has not displayed the question till recently. All right, never mind. So here we are talking about recommendation engine. So first you pull the data from your web server, then you clean it up using Pig and Hive. Then after you have cleaned it up, let Mahat, the machine learning library, generate the outcome and give it back. So in this scenario, what you must understand is that we needed five components, meaning five things need to be executed in a sequence, and every day these need to be executed. It's not humanly possible to do this without making mistakes. Therefore, you would require component like Uzi, component like Uzi to help you with scheduling. So Uzi will make sure that all these five things get executed every day on time. Okay, and then rest is just interaction part. All right, great. So this was the overview of Hadoop ecosystem, and then now we'll go through the now we'll go through the CloudX lab, and then we will go with HDFS. All right. Okay, very good questions. Let me copy paste. Ila's question is, isn't MapReduce step number two? It can be. Yes, it could be I mean, it could be step number two. That's very right. Okay, so generally maybe you have 2.5 here, or maybe 1.5. As soon as you pulled the data, you realize that you can't really clean it using Hive or Pig. So first you write some Java code to format the data and then start processing. Or maybe 1.5. I mean, it all depends on the kind of data you have. If it's standard data, say it's the data is coming from Apache logs, so you have Apache log parsers which can convert it into a tabular format. Okay, if it's coming from an unknown source, you might have to write a Java code to convert that incoming data from the sources into tabular format or any other structured format like JSON or something else. All right, so Yogesh's question is Uzi like auto sys scheduling? Okay. So as far as I know about auto sys scheduling is, yes, it's basically execute a schedule from time to time. Yes. Plus like make or and or Maven. Okay. So it's not only scheduler but also helps you create the full project graph. All right. Another question from one question from Ashwini. Okay, let me just copy. Okay, here's his first question. If we are using HBase, in that case, are we not going to use HDFS? Okay, so basically, it goes like this. I'll draw it. That'll make more sense to you. Okay, so this is you, and okay, and this is the files, the HBase. Let's say HBase, and this is HDFS. Okay, so You talk to HBase in terms of rows and columns, okay, saying can you update the particular column of a particular row, okay. So the way to you HBase will look like, okay, there is, it has got tables and rows and so on, right? While in HDFS it's a big file where you keep on writing into the file, okay. That's how it looks like. Now HBase internally would convert this table into HDFS and save it. Make sense to you now, Ashwin? So yes, so indirectly HBase is indirectly using the HDFS. Okay, great questions. On top of HDFS, only all the other components will come. Yes. All right. Uh, question from a further question from Ashwini is, um, okay, looks like there are one Ashwini and one Ashwin in the class. Okay, and the worst part was in my one class, there were two persons, both with Sukhvinder Singh name, two different persons with the same first name and last name. Okay, so it became quite difficult for me to figure out which one I'm talking about. All right, so HBase will convert structured data into unstructured data into, no, it will not. Okay, we will have to do that. Okay, we will have to do that using Pig or Hive or some other tools, or MapR or some other tool. Okay, a question from Stanley. If we use HBase without HDFS, how will the data be stored on the disk? Quick answer is that quick answer is that HBase only works with HDFS. Okay, and I'll give you an overview. I'll give you an overview of how does HBase stores the data in HDFS. As we go forward, there is one detailed chapter about it. Okay, so don't worry, we'll talk about it in session number 6. Yes, rows and columns mean structured only. Yes, so the idea is here, it's us. If you see, this is us. When they talk to HBase, they talk in when we talk to HBase, we talk in terms of row and column, the way we talk to MySQL or we talk to MS SQL. And HBase internally is storing data into files. The way you have MySQL, which is creates one file for each table, similarly HBase does a similar thing with HDFS. Okay, but HBase by itself will not convert our structured data into our unstructured data into structured data. It is us who has to convert that unstructured into structured. All right. So when we want to do, say, when we want to say things like add it, okay, update, update a column and set its value to X. Okay, something of this sort. If we have to do this kind of thing, say update a column and set its value to X, then we ask HBase and get the work done through HBase. But when we talk to file, we say that delete a file, append a file, or create a new file. Okay, so that's the difference between our behavior towards HDFS and HBase. Because HBase talks in terms of rows and columns, and HDFS now talks in terms of files. As we use both the things, we will get thought clarity on both. Okay, so so do I make sense, Ila? This is a very high level overview of the whole ecosystem. Okay. Okay, no worries. Basically, the difference between HDFS and HBase is similar to the local file system. Like you have C colon, it has folders, and there is a database like MySQL and MS SQL. So it's the same kind of a difference. All right. Now, all right. A question from Amrutan. It's a good question. So this is something which we have not discussed. Okay, so just give me 2 minutes. Let me cover other questions and then I'll give you an overview of Zookeeper quickly so that we are not, we are not too much in the waiting mode. Okay, so I'll just give you an overview. All right. Okay, good. Did I answer your question, Stanley, regarding the HBase without HDFS? All right. So, okay. Okay. So I think the other very good question from Ying Mi. Okay. Question is, can you give an example when data is pushed from Scoop to Hadoop and back? Okay. I'll give you a very interesting example which we used similar to like Scoop at Amazon. Okay. So I'll try to draw it just to make it little more lively. Okay, so let's say at Amazon we have many web servers, right? Because Amazon.com serves the data from many web servers. This is your web server fleet. Okay, we call it web server fleet, meaning multiple web server lined up to serve you. Okay, so these are your web server. Okay, so here it is. So this is server 1, 2, 3, and 4. Okay, so all of these are serving the user. All of these are serving the users. The users are sending requests for the website and they are serving the user. Okay, and all of these, as in when the when they're serving, they're writing logs to the file system. They're writing logs to the file system. Let me draw a file nicely. It's like, okay, so okay, so all of these are basically writing logs to the file. Okay, the, this is like I'll call them logs. Okay, so all of you don't worry about time running out or anything, because these are very brilliant questions, and it's not a good idea to skip these questions, because we are here to discuss these case studies so that in practical life you can utilize these. Okay, so I would not hurry up to skip these questions. All right, so okay, so let's say you have got this. I mean, this is a true case study from Amazon, and these tools like Flume are kind of unsung heroes because these are really used in production environment. So you have at Amazon we had this full web server fleet, and all of these web servers were continuously writing the log. And what does log mean? Which request came, what was the URL parameters, what was the session ID, and was there an error, what was the debug message that happened. Now, at Amazon, we did something very important. What we did was we provided our customers great support, and that was at very various levels. So, and how does it relate here? So but that does not mean when we say we are going to provide the end user a very stable, nice interface, a great website, that does not mean that we will not run the experiments. We will run the experiments in a way that it is mostly harmless. Okay? So, from time to time, every day, there will be at least 100 check-ins, at least 100 modifications in the code of the website, and that will be pushed to the main production area. Okay, but those new changes will be visible to only say 1% of the total users. And as soon as those new things are happening, or any other errors are occurring in the production, so the web server logs will start having those error messages. Now, it was very important to note down that what are the error messages right now happening on all web servers. So all of these web server logs have to be brought to a single machine. All of the logs have to be brought to a single machine, and there so all of these logs, when they're brought to a single machine, we can simply say that uh, so let's say error in invoke.java .jsp at line number 34. Let's say this is the error occurring, and we are seeing that this error is occurring say 100 times on multiple machines, because we have gathered this information from all the servers parallelly. Okay, and we notice that this error is occurring 100 times on the servers. Okay, so we provided at Amazon, we were provided a tool which showed us that how many times a particular error message is occurring on all our web server fleet. Okay, so this essentially means that in real time we were pushing the data and we were analyzing the logs so that we can predictably figure out that there is something wrong with a particular piece of code. Okay, now it's very clear that somebody has pushed invoke.jsp recently, and because of which it has broken at least 100 times. Okay, so these kind of error messages will be invoked, and if there is a error message, something like invalid javascript object, and it has occurred only one time in last 1 hour. Okay, that means it's not so severe, and therefore we don't have to worry about it right now. Okay, while the first error is occurring 100 times. And how did we figure out? We first pull the data continuously. We keep on pulling the data continuously from all the servers and keep on analyzing that whether something threatening is happening on servers or everything is all right. And this is one use case where we use Flume continuously. Okay, all right. So actually, I read it like a Flume, but it was Scoop. Okay, so this was a use case of Flume. You can make a note of it. This is an interesting case study. Now, with respect to Scoop, Scoop was okay. The case with Scoop was simple. Uh, okay, when data is pushed from Scoop to Hadoop and back. All right. Next question is what are the cases where we pull the data from the structured data source, and then once we are done we push it back. Okay. Let me take a small use case. Okay. Let me take a small use case again. Okay. This time I'm taking the case of Scoop. So you have got, let's say, a small ticketing system whereby all your customer support logs the tickets. Okay, now you want to figure out the reasoning behind ticket, or you want to just bucket all the tickets into four buckets. Okay, generally let's say you want to figure out what are those common four kinds of tickets that happen mostly. Okay, so you would like to bucket most of these tickets, right? This is called clustering. Okay, clustering. And clustering is difficult exercise. You want to bucket just the way you have Gmail is classifying your email into social, promotion, inbox, and updates. Similarly, let's say you want to bucket automatically these tickets into some random four buckets. That's called clustering. Okay, so you want to do the clustering of your tickets as in the support call, support request. I believe everybody is familiar with the ticketing system uh, for managing the customer supports. Now you want to figure out four major classification of the tickets, or say 10 major classes. That's called clustering. For clustering, because clustering is a difficult exercise, it's not possible to run clustering over say 10,000 elements using a single computer, and the results will not be very interesting, or will not be, will not give you a great the if you run it on single machine, you won't get timely results. It will take a lot of time because clustering is a very intensive process. So for clustering you might want to first pull the data using Scoop. Okay, so ticketing system is say it's storing data in MySQL, or maybe there is some API or something. So if it's say ticketing system is running storing data in MySQL, you want to pull the data using Scoop. You want to pull the data using Scoop into say HDFS. Okay, into HDFS, and then from there you want to run Mahat. Okay, you want to run Mahat. Now Mahat will again store the data in HDFS. I could have drawn it. Yeah. Okay. Mahat will take input from HDFS, store back into HDFS. So these are the results. Okay. These are the results of clustering. We will give you an example of recommendation, and then so once the results are here, then you might want to show it to the user, or represent it in your BI reports or something else. So these are the results. Now you could push back these results into MySQL using Scoop. Okay, so this is another use case of okay. So, I can actually pull it here. So for clustering, you can use Scoop. So this was one use case where I'm trying to explain why Scoop will be used for in and out. Make sense to you now? Yingming? Yingmeng? All right. I'm so sorry for misspelling. Okay. So Yimang, am I able to explain? Great, great. All right. Let me store these somewhere. Okay, so that they are not lost. All right, I'll do that later. All right. Okay, I'm not great at this. Never mind. So let me try to answer other questions. Great. So Prem, did you get your answer to the question? Hive does not talk to HBase? Yes, it does. Good question. So Hive does talk to HBase the way it talks to HDFS. All right. So Hive can analyze data stored in HBase. Similarly, Pig and MapReduce both can analyze data which is stored as tables in HBase. Okay, this one I think we have talked about this. So I will say HDFS. Okay, I'll say HDFS is must for HBase. Okay, is the other way around, but not HBase is not required to run HDFS. All right. Um, okay. Uh, so Sasti, did you get the answer to your question? Can you give an example to differentiate between HBase and HDFS? Okay, another question from Ella is, are we going to use later where Mahat reads HDFS and then yes, we are going to take a case of recommendation. Okay, all right. Wow, this is a great set of questions. Great. All right. So, all right. So that was a quick introduction of the various components of ecosystem and uh, couple of case studies quickly. Now let's first go through the environment overview, and then we will go through the HDFS. All right, or you want to go through the HDFS overall HDFS first? All right. So let me open No Big Data. So when you open No Big Data and you log in, you might see something like this. You can click on my courses, and once you see my courses, you can go into this one. Okay, so be ready that the course might expand into around 15 sessions, 14, 15 sessions, because the course, as we declared earlier long back, used to take around 12 sessions because there were many topics missing. We have expanded more and more to include the latest components such as Spark streaming, and all other things. Okay, so therefore it might go up to 14, 15 sessions, so be ready with that. And here you see these details which are for your CloudX lab login and password. So either you can go to Ambari. Ambari generally shows the status of the whole cluster. Okay, so you can see that there are 5 data nodes alive. You will understand what is a data node, and what does it mean by a disk storage, and what kind of cluster node we have, how much memory is being used by name node, and you will understand why does name nodes heap matter so much that it's on the front. Okay, and the name node has been up for 16 days here, and so on. These are the various details you can see here. All right, and these are the various components of the Hadoop ecosystem. Most of them are here, but there are some such as Spark which is not being mentioned. Okay, here it is. Okay, so we'll go through most of these tools. Right, we will learn how to use individual and what is their significance, and the use case. All right, same username that's being displayed here has to be put into the Ambari. Okay, same this user login password. These are CloudX Lab login passwords. Okay, not the LMS login password. Yes, Sasti. So when you click on Ambari, it will ask for user ID and password. Enter this user ID and this password. Either you can click on show. I'm not going to show my password here, or you could just click on copy to clipboard and paste it there. Okay, double click the login and then you can copy paste. All right, in case you are not able to log in, click on show and then maybe you can type the password. Okay, so Ambari is a good question. Thank you, Yogesh. Let me explain. So Ambari is for mostly the administration part. So when you install Hadoop cluster, you install it using Ambari, and basically you can provision Ambari. Okay, say you want to change the configurations, you want to increase the RAM, increase the memory, or you want to add more hosts into the cluster. So if I'm an admin, I'll get a add hosts into this. Okay, so that so Ambari is a way, an interface for the administrators. Although in the newer versions of Ambari, they're providing the provisions for running the Hive query and others, but Ambari is largely the UI for the admins. Okay, so Ambari is great for provisioning and administering. And then you have Hue. Okay, so hue is quite important. Okay, so hue lets us interact with all components from Hadoop ecosystem. Other difference between Ambari and Hue: Ambari is from Hortonworks, while Hue is from Cloudera. Okay, so you have data browsers. You can interact with HBase and Zookeeper and Scoop through the browser itself. Similarly, you can interact with Hive, Pig, and Spark and Oozy from the browser itself. Okay, so this is Hue. You can talk to anything. Let's say there's this file, you want to download it, you can download it, and you can upload a file. Okay, you can upload a file, and that should be it. Okay. Okay, so basically you can interact with all the Hadoop components. So if you are going for administration, go through Ambari. If you are you are developer, data scientist, analyst, or anybody who wants to interact with the components, you want to solve their problem by running these tools, you should be using Hue. And if you are you are okay with the command line, then we give you the complete access to the cluster using the console. Okay, I am logging in using this login password. Console is a place, this is basically a login to one of the Linux terminals which we have right now. And it's, if you have Linux, you can use SSH. If you want to directly use Windows, you can download Putty. But I'm more comfortable with the web-based one because I don't have to install anything. Therefore, it's better to log in through the browser itself. Now, what's the use of this console? From here, you can actually do everything on this machine. Okay, let's say you want to write Python. Okay, you can start writing Python. Okay, Python code. You have some Java code and you want to compile, you can do that. And for me, it provides R as well. If you are from R background, you can run R. Okay, Control D, and Control D exits from most of the tools. Okay, so from here I can interact with almost anything. I can see what's running on this machine. Okay, and I can practice my Linux commands. These are my Linux command. Also, please note, when I say ls, it gives me the list of files. Here it's giving me the list of files, but this list of files and this list of files are not the same. This list of files are from the file system of e.cloudxlab. That's a single machine, while this file system is Hadoop distributed file system. Okay, so this particular file may not be existing here. When I say ls here, ls means, okay, ouch, ls means list the files. The way you have dir on Windows, on Linux it's ls. And using this console or the command line, you can actually interact with the local file system and run any program, be it Pig, Hive, Spark, and anything you can run from here. Okay, so I'm into, this is the Pig console. Here I'll be executing Pig queries. Okay, you can press Control D and get out of it. Similarly, let's say you want to run Spark console. You got Spark here, you can start working with Spark immediately. Okay, so you have got the full environment ready for you so that you can start working on the Hadoop right away. All right, very great questions. Let me answer those before proceeding. Question from Yogesh: Does Ambari also install Hadoop ecosystem all new nodes? Yes. So this is the great way of installing Hadoop is by using Ambari. All you do is install Ambari on one machine and tell the Ambari the login password of all other machines, and it will go and install everything on the whole cluster. Okay, so and also tomorrow if you're adding more and more nodes, you don't have to install Hadoop on the new fresh nodes. Ambari will do it for you. You just tell Ambari that, hey, these are the new nodes, can you install Hadoop? That's it. All right, great question. Quick question from Sasti. What is R? R is basically a small programming language for churning the data. Okay, churning the data, and it has probably the biggest set of libraries available. You'll get the libraries for machine learning, you will get the libraries for social science, you will get the libraries for data downloading and whatnot. So R is basically a data oriented language, but it is used in almost all kind of circumstances. And should we learn that as well? It all depends up to you. Okay, but I would recommend, instead of learning R at this point, if you haven't learned Python, then you should learn Python. Okay, why I talked about R and why we have installed R? Because many people in this group want to go for data science, and for data science R might be required. Okay, a question from Yimang. Do we have sudo access on Linux terminal? And no. And because if we have sudo access on Linux terminal, it's going to damage the file system and everybody, because there are many users on this. So if you want the full control, you are looking for complete control, uh, i- okay, install VM. Okay, so go through in case you want to install. Okay, so in case you want to install Hadoop, as in on local machine, go through these installation instructions. Okay, and in case you are trying to install on a big cluster, use Ambari, and here is a good documentation. Okay, this is how you start. So this is how you will start. First you will install Ambari on one machine, and then you will start Ambari server, and then you will start deploying on the network. Okay, so this is for cluster. And if you first, you can actually start with CloudX Lab, you don't need it. But in case you really want it on your own machine, then you can basically install a virtualbox. Okay, you can download we prefer the Hortonworks VirtualBox over Cloudera, and this VirtualBox is around 10 gigabytes, and it takes around 4 GB RAM. So be aware of that. So you might require a high-end machine. Laptop might not be sufficing, because most of the laptops do not have RAM beyond 4 GB. So these are the instructions. Go through these instructions, and you shall be able to install Hadoop on your own machine. So this is just optional. I would strongly recommend that you use Cloud Lab more than the virtual machine. Okay. One question from Ritika. For a new person, is there a cheat sheet for Linux command? Actually, you can. I did have a cheat sheet, but better cheat sheet is, yeah, the first one that comes is actually pretty good. This is not looking good. Yeah, this one is good. This one is good. All right. All right. So when you're going through these things, we'll go through one more topic here. Regular expression is must. Okay. Do go through these regular expression session. Here there is a video. Okay. And also on the second session there is file system of Cloud Lab explained. Do go through that one. That's a very important one. Okay. All right. So in case you do not have, in case you do not have much idea and you're getting stuck with Linux command, feel free to drop us an email. Okay, one of us will help you out, or drop us. Okay, so also we'll add you to the students' Facebook group. Facebook for some reason did not allow me to add all of you, so I'll add you very soon. Okay. All right. So this is good enough. Wow, there are so many cheat sheets for Linux. So basically, the first few things you need to know about Linux is one, how does file system looks like? Okay, and second thing you need to know about the basic commands to move file, change directory, and create file, nano, and those basic commands. All right. Now we that's I think good enough. So go through this particular link whereby we talk about the uh, uh, difference between the various file systems, because one file system is on your local machine, as in local laptop. Other file system is on this machine, e.cloudxlab, the ls minus l. These are the files. You see the last column is the files. See, and this is the owner group and the various permissions along with the size of the file and when it was created. Okay. All right. All right. Ritika's question is, does data scientist interact with Linux command? Not many, but I recommend that people should be aware of Linux command. I have met some data scientists who were only comfortable with uh, R. They were not great with Linux, but in my personal opinion, I'm saying personal opinion because there is no way to prove that I'm right. So, in my personal opinion, I feel that people should get comfortable with Linux commands, because almost every Hadoop cluster, or you can say almost every big data cluster, or on the server side, Linux is still the prevalent operating system. So for a great career in any of the data oriented technologies, you should get yourself familiar with the backend, with the Linux file system as well as the Linux commands. Okay, so all right, do I make sense, Ritika? All right, that was a overview of the Ambari Hue and the console of the CloudX Lab. All right, so also if you go to CloudX Lab and you want to say extend your duration, say for example here I can click on extend, and that should be good enough. Okay, so yeah, and by default you will be logged in to CloudX Lab, because here it when you go to our LMS, you automatically get logged in into CloudX Lab. Okay. All right. Another good question from Yogesh. Question is, do we have any sample files in CloudX Lab? I will say CloudX Lab. that we can work on with basic commands. Yes, yes. So what we have done is we have put the data in HDFS in the data folder. Okay, here there are various commands related to various folders related to various topics. You can use this kind of data in slash data in HDFS, not in the local file system. All right, but my folder, okay, my folder, let me open again. Let me open the console again. Where did my copy login and copy password? Okay, so here also, my folder, this particular folder is accessible to all. If you want to copy some data from my folder, you can copy from there. Okay, that you can use. All right, there is nothing private from my students. All right, so that's a overview. Yes, and I'll correct the spelling of CloudX Lab. So yes, you can upload any data from your local machine to CloudX Lab through internet by any chance. Yes. So there are two ways. One, you directly upload the data into HDFS using the browser, using the Hue. Second is using WinSCP. Okay. And second is using WinSCP. Okay. To into the into what machine was that? D dot I think E. Where is your console? Uh, okay, here. Okay, so using WinSCP, you can upload the data into e.cloudxlab, while using Hue, you can upload it into HDFS. Okay, so Eli is saying that can you log in into Hue? Okay, here in Hue, you can go to file browser. Just take the cursor just below this, and then it should be okay. Otherwise, in case that's not clickable, sometimes it's not clickable, you can actually go to slash file browser. Are you able to go now, Ila? Sometimes this is not clickable for some reason in some browsers, and in that case you can directly go to slash file browser. Okay, and here there are various tools. As we go forward, we will see more details of these things so that you have more thought clarity of what we're about each of these components. All right, great, great. Was I able to answer your question, Ella? No? Okay, let me just log out and show you again. So I've logged out. Now, in my LMS, you see this login. You paste the login here, and then you copy the password, paste the password, And when you log in, you won't see anything like this in your case because you may not be having any workflow. So you might go to file browser. Okay. In case file browser link is not working, you type in the console window, say d.cloudxlab/file browser. Okay. All right. All right. Next is, now let's start with the very basic problem of storage. Okay. So let's start with a very simple question. The question is, say you want to store 100 terabyte of data. You want to store 100 terabyte of data. How are you going to build such kind of a file system? Say you are living in a hostel or living in a society, or in your office you decide that you will build the biggest movie hub which can store almost every movie inside your organization. Then you might require 100 terabyte of storage. How are you going to build such kind of file system? Of course, we can simply answer that we will buy the space from Amazon, but the question is, what if you are Amazon? Okay. So question is, how will you build such kind of file system? Okay. Okay. Very good answers. An answer from Ashwini is, we'll break the 100 terabyte data into small chunks of files and then store. Okay. Stanley is saying distributed file system, and Yingmei is saying with clustering. Okay. Okay. So distributed file system is what we are going to go to eventually, but if you have to do right now, what is it that we are going to do without the knowledge of any HDFS? Yes, Kathy. Kathy is saying that we are going to store in data nodes. Yes, but let's keep these questions, okay, these two answers as little more mature answers. What if we have no knowledge about HDFS? Okay. Ashwin is saying that we can store it in traditional databases. Okay. The storing a movie into database is quite expensive affair. Okay. All right. There is a good answer from Sasti. Buy hard disks. Buy hard disks. Lot of them. Okay. Go ahead. Go ahead. I want to see this answer. I want to see this answer. Yes. And let's say we buy a lots of hard disks. Let's say how much, how many hard disks do you want to buy? Say 100 hard disks. Okay. Or maybe 200 each of, say 500 GB, zero point 0.5 TB. That's okay. Now, okay. Eli is saying that without HDFS on supercomputer, if there is one, okay, yes, we can store. But a supercomputer also, you will be amazed to know that supercomputer is not, at most would be having say 10 TB, and they'll be flaunting this hard disk. And yeah, yes, okay. Liu Song is saying that using Flume to transfer data, good. Okay, okay. Ashwin's question is good. Storing the data into shared drive on the servers. Okay. Okay. Yes, that's right, Stanley. So we are going to slowly go towards distributed. But before jumping on to HDFS, or say a mature answer, let's try to build a rudimentary distributed file system. Brilliant, brilliant answers. Here is an answer from Mahesh, using NAS or SAN. Okay, very good answers. Abru is saying perhaps create a library of storing the files first. Okay, brilliant, brilliant set of answers. Please keep the answers coming. I'm not seeing the answers from everyone. There are only answers from few. So feel free to give the answer whatever you like. And I'm amazed at the answers every time I get in the class. Okay, so some of the answers are so amazing that uh, while we were discussing our first session, somebody suggested a different kind of file system, and that's a new file system that has come recently into the open source world. Okay, so feel free to answer whatever you have in mind. Do not worry about whether you are right or wrong. Okay, so the problem is very simple, and probably all of you must have faced this problem. Yep. Ashwin is saying storing in the cloud. Okay, okay, great. Sumai, Amrutan, Ravi, Kulbir, Kati, Lokesh, Lakshmi, Lee. Feel free to answer. I'm looking forward to your answers. This is an answer from Stanley. I'm going to put your answers together, Stanley. Prem is saying using SSD for fast access. Okay, most of these answers are relevant. Okay, are relevant. So I would like to explain these answers to everyone. Okay, a question from Lee. Using banks of hard disk in SAN arrays. Brilliant. Thank you, Lee. All right. All right. So SSD means solid state hard drives. SAN means storage area network. NAS means network attached storage. Okay. So and DFS means the distributed file system. Okay. Now, so the answer which some of you have answered is build NAS or SAN. NAS means network attached storage, or SAN is a these are standard terminologies for building a file system before Hadoop came into the world. Okay, so and you will be amazed that when in 2002 we were working at Disha, we built a similar kind of file system using our own ways. Okay, so we had a systems team, and we developed these kind of file system using many hard drives. Okay, so What we did was we bought lots of hard drives, connected these hard drives to many computers, and connected these computers to a single machine. Okay, so this is how it would look like. If I have to build simplest one, I'll buy 100 hard drives, and I will call them drive 1, drive 2, drive 3, drive 4 up to drive 100. And then on one computer, say the computer number 1, I will connect or net over the network, I will mount these drives so that when a user comes to this computer, he sees all the hard drives available here. Okay, as a redundancy, I could keep another computer which will have the same drive 1, drive 2, drive 3 up to drive 100. So this each drive there'll be a folder with the same name. So when a user wants to store, he will see 100 folders, and user can store in any of the 100 folders. Now, question to all of you: do you think there is something wrong with this? Or question is, do you see problems in this kind of device, this kind of architecture? We have taken 100 hard drives, connected to these computers, one hard drive in each computer, and then connected these computers together, and then made an arrangement, made a folder look like it contains 100 more folders, 100 folders inside it, each folder representing each hard drives. Okay, or hard disk or hard drive is the same thing. Okay, so question to all of you is, what is wrong with this style? Okay, a question from Ashwin: does Google Drive, Dropbox, etc. use Hadoop? I'm not sure, maybe. Okay, a question from Stanley. Okay, it's not a question. Okay, so Stanley says that this will cause a traffic congestion. Good, good, keep going. These are good answers. Sasti's answer is cost and time. Time as in the speed of reading the data, brilliant. Ravi's answer is the data consistency issues, brilliant. Ravi Kotu's answer is one fails, the whole system is failed, brilliant, brilliant. Ashwin's answer is it's expensive, and every time data is full, need to buy a new one. Yes. Okay. So it's expensive because every time it gets full, we have to buy a new one. Okay, that's one way to look at it. Now, and the one of the problems which Kulbir is suggesting is there's no backup for files. Brilliant. And Amrutan says that missing high availability. Great. Mounting hundreds of drives is an overhead. Thank you, Ashwin. Good, good. And Mahesh is saying that if one hard drive fails, data can't be recovered for that hard drives. So there is no fault tolerance. Katie is saying that I think connecting all 100 folders directly to one may create a bottleneck. Yes. Prem is saying finding what drive is stored on. Good. Which data is where? That's another big problem. Thank you, Prem. Sumaya is saying that it's very expensive to follow this structure. Yes. Abru is saying read write between different boxes will slow down things. Yes, it's similar to Stanley's answer. Good, good. Ron's answer is difficulty accessing similar data across drives. Good. Ashwin is saying space may not be utilized properly, like some space is not utilized properly. Brilliant, brilliant. I think almost every point has been answered. Let me try to summarize. Amritan says may be difficult to scale in future. Brilliant, good, great. These are good answers. All right. And Sasti's answer is data integrity issues. Ravi is saying concurrency issues. Brilliant. Concurrence issues are something which we forget all the time. Brilliant. Okay. So let me minimize this thing and this thing. Okay. So great set of answers. I'm impressed. All right. So you have actually answered all the questions. All the points have been kind of answered. So okay. So this is a summary of what all of you have said. Let's go over this summary and try to build a better system as we go forward. Okay, so let's take a break for 10 minutes and back by 9:42 p.m. IST. All right, so let's start. Is everybody back? Should we start? All right, so I hope everybody's back and okay, great. So in the first half, we were discussing the problems with connecting the 100 drives in the network and using that as a file system. So the main problems which we came up with, one, the failovers and backups were not great, because if any of the computer fails, any of the node fails, the data on that node is no longer available, right? Or even if the data is not completely lost, let's say there is something wrong with the network, but the data is no longer available. There are two parts to the data. One is failover and other is backup. Backup means the data is available somewhere, we can manually recover it. Other is failover. In case that particular data is not available, do we have alternatives? So neither failover nor backup was right in the previous design. That was one problem. Second was, I mean, and when we say backup and failover, it is to recover against, it is a defense against many kind of problems. A problem could be the hard disk is corrupt. The problem could be the there's something wrong with the operating system. The problem could be there's something wrong with the motherboard or any other component of the computer. The problem could be the CPU, the power supply is has burnt in a computer. The problem could be the network cable is no longer working, or something is wrong with the network cable or network connectivity. So there could be many kind of problems that could happen with the individual node, because of which the connectivity might get lost. So do we have that kind of defense in the previous architecture which we discussed? The answer is no. Neither we have failover nor we have backup against that. Next is, how would you distribute data uniformly? Let's say we created 100 folders. Now, how would you ensure that data in all these 100 folders is uniformly distributed? Because let's say you came up with a scheme that, let's say, since we are storing movies, let's store all the movies starting with A in the drive 1, B in drive 2, and so on. You come up with some kind of schema saying for S, for alphabet S, we could have like 3 computers dedicated to it, and so on. Or maybe we can say that let's dedicate 3 computers to each alphabet, and we make kind of a diagram saying from this to this goes into this computer and so on. But does that guarantee that the data will be uniformly distributed? Most of the movies start with the or a, the or a. Most of the movies are starting with those letters. Therefore, the servers which will be dedicated to the or a would get full very quickly, while the other servers which will be dedicated for the letter, say, Q, will be free. Therefore, coming up with architecture or coming up with a distribution where we can divide data uniformly across the cluster is going to be difficult, and it's quite painful. There's a human intervention required all the time. The human intervention is required all the time in order to keep the data distributed uniformly. I remember one of the nightmares where we keep on doing this shuffling all the time. Okay, and I remember some of the admins used to just delete all the movies and so on. So basically data distribution will remain one of the problems. Second, next problem is this the best value for money? Because if we go with the cheaper hard drives, you might require more hard drives. Okay, or if you go for cheaper hard drives, the chance of failure might increase, and therefore you may not like to use those cheaper hard drives, right? Next is, what about increasing accessibility? Okay, I mean, what about increasing accessibility? One of you have answered this question, also have raised the same point. Let's say today is Independence Day and everybody wants to watch the same movie. The same movie is stored on one computer. Now, when multiple people are trying to watch the same movie, what happens is that those servers that contains the movie will get overloaded, or it'll be a single machine, right? A single machine storing the same movie. Therefore all the people would try to read the movie from the same machine, and therefore therefore that single machine will not be able to give you the great give you the output, because when multiple people are trying to read the data from same machine, what happens is uh, it get choked. Okay, it will get choked because hard drive is a physical device. There is a header, there is a which keeps on moving back and forward, and the drive keep on rotating. So if you look at a hard drive closely, only one person can actually read at a time. If you do the back and forth too much, what happens is the header gets the drive gets scratches, and it is quite inefficient. Therefore, accessibility is probably the biggest bottleneck in the previous architecture. Because as we discussed in the session one as well, that reading data from the disk is quite slow. Reading a terabyte data takes around 6 hours on a fast hard drive. Therefore, accessibility is going to be a very big issue. Although accessibility is solved by using drives like SSD, solid state drives, where data can be read concurrently and in a very fast manner. But then the volume becomes an issue, because solid state drives do not have the header which moves back and forth. But solid state drives are very expensive. Therefore, therefore the volume will become an issue. One, they're expensive. Second, they're generally smaller in size. One another next point is scaling out. I think one of you have raised this point. One of you have raised this point. What about scaling out? What does it mean by scaling out? Scaling out means today you need to store 100 terabyte data. Tomorrow, or maybe one month afterwards, you might need to store 150 terabyte data. At that point of time, adding more hard drives uh, to the cluster, how difficult it is going to be. How will we make sure that as and when we are buying hard drives, we keep on adding those without too much of hassle? So based on these problems, to solve these kind of problems, Google came up with Google File System, and the same was implemented by Hadoop team, and they called it Hadoop distributed file system. Okay, are we all on the same page? Do you want me to repeat something which we have discussed so far? I'll be happy to repeat if there is some anything which I missed, or anyone is feeling uncomfortable with something. So basically, this kind of architecture is inefficient for various reasons. Okay, and therefore, and these kind of problems are solved by Hadoop distributed file system. Okay, everybody comfortable with this? Should we move on? Great. All right. Now, so that was a general overview. Okay. So now, as we go forward, keep these few questions in mind, that how will you distribute data in a nice manner? How would you utilize so many computers parallelly in order to store? And there are many more questions that will come to. I mean, whenever we are thinking about a feature here, talking about a feature of HDFS, you think about these few problems. Okay. Okay. Good. Good. So the Hadoop distributed file system is a file system for storing humongous data. Okay, it's it's for storing humongous data and having a great redundancy, and and giving you great read and write speed even on huge data. And how does it happen? Okay, so the main architecture is that it is made up of two kinds of nodes. One is called admin node, and then there are rest. And those rest of the nodes are called data nodes. Okay, so before we start thinking that it's a physical hardware, let me clarify. The name node or admin node is a process, is a service which keeps running on a machine. Same is the case with data node. Every data node is a service which keeps running in the background. For example, the mail server, when we say mail server or a web server, in the same way you have name node as well as data node. These are the servers which listen on a port and you talk to them. Okay, so these are the services. Name node is one service and data node is another service. Okay, so the main part in this ecosystem is name node. What is name node? Name node is kind of the main supervisor of the whole ecosystem. Okay, we will talk about name node failover and everything in detail. So name node is somebody who you talk to first. Okay, he is more like a supervisor, or you can say warehouse watchkeeper. Okay, he's a watchman of a big warehouse, and this warehouse is contains many data nodes. Okay, so this admin node keeps the record of what is where, which file is on which machine. Okay, admin node keeps the record of the information of every file, and that's called metadata. Like, what is the name of the file, what is the name of the folder, and name of the folder, name of the file, size of the file, and so on, attributes of the file, and so on. And it's a service, as we have told, and all of this is loaded into the memory. Okay, it's loaded into the memory. Why? Because it needs to answer to the customers very quickly. Whenever you go to name node, it will respond to you very quickly. You go to the name node saying, hey, can you tell me where is this file? And name node will give you, okay, go to this data node and talk to him. Okay, now the data nodes store the actual data. Data nodes have no clue about file name. Data nodes have no clue about full file size, but data nodes store the actual data. Okay, all right. Now the next bit to understand. So in HDFS, HDFS is made up of one name node and many data nodes. Okay, one name node and many data nodes. Name node keeps a kind of a is a bookkeeper for you who keeps track of which file is on which data node and so on. Okay, and data node store the actual data. Now the next bit is very important. Okay, because in the first case you will say that how is it different from our architecture. Okay, how is this different from our architecture, right? Now these next few features will make you realize that there are few things which are different. The files are not stored as such. The files are broken into pieces. While the files are being written at the time itself, the files are broken into blocks, and these blocks are generally of 64 MB. In our case, in Hortonworks, the way we have configured, it's 128 MB, while in Cloudera, the default size is 64 MB. You can configure your own size. Okay, so every file gets sliced into the chunks of 128 MB, and then and those chunks are stored on data nodes. Okay, so now what does it mean? It means that a file might go to multiple machines for the storage. A file might be stored on say 20 machines, right? But keep in mind that one particular data node can contain all the blocks of a file as well, based on the storage available and so on. Okay, now what's the benefit of blocks? One, as somebody raised a topic that it might not full the disk properly, right? In our kind of architecture that we discussed before starting SDFS. Yes. So basically, let's say we are putting some data on data node 1, we are trying to stuff it with more. Okay, so the maximum amount of storage that could go waste is around 128 MB on each node. Let's say on data node 1 only 127 MB is available. Then we can't store any more blocks. So at max, every data node can waste around 128 MB, lesser than 128 MB. Okay, so that leaves less unused space on the disk. Next, it optimizes data transfer. As we will see that what happens when we add more machines, so these blocks move to the next machine so that the equilibrium arises, a point where all the nodes are equally loaded. So that optimizes the data transfer. Next benefit of having blocks is it distributes load to multiple machine. So 1 GB file, let's say there's a movie of 1 GB, it'll be stored on 8 machine, which means around 8 people can happily watch the movie if they are watching with a 5 minutes difference. Okay, so let's say I started watching a particular movie. After some time, you also wanted to watch the same movie. I might have covered for finished first 128 MB, so I might be using some other machine, and you might be using some other machine. Internally, that's how it happens. Okay, so this is how slicing a file into blocks helps us in save the space, distribute the load, and optimize data transfer. Optimizing data transfer, will come to it a little later. Okay, for now you can understand it. When we add more storage into this, when we scale out, only few blocks will move, rest will remain as such. All right, now a few more questions about this block size, because there are many. First question that comes is, who slices the file? Who takes the responsibility of cutting the file? And then when we try to retrieve the file, who merges it? The answer is client. The client comes to the admin node, says that, hey, I want to store my file. Okay, admin node says that, okay, from 0 to 128 MB, put it on data node 1, and from afterwards 128 MB, put it there. So the client, the one who is trying to store, it's his responsibility to store the data. Whether that client wants to do it parallelly or in a sequence. Okay, it's up to the client whether he wants to do it parallelly or in the sequence. Meaning, it could open three parallel threads and then start reading the same file using multiple threads parallelly, and send it to multiple data nodes. Okay. Okay, so I will cover one more bit and then try to answer your questions. Okay, I'll cover two more slides and then we'll discuss. Next is the very important bit is replication. Why? Because one of the things which our cluster suffered, the cluster which we built, was backup and failover. It did not have any backup. Okay, now this new architecture, Hadoop distributed file system, solves that problem using replication. Every block has got three copies. Every block is copied on three machines, meaning two more copies are kept. Okay, this replication factor is configurable per file, as well as you can set the default replication factor for your file system. And the other important bit about replication is that no two copies of the same file are on the same machine, because every machine is considered disposable. At any point, any machine can fail, and there could be any number of problems that could happen to the machine. Therefore, every block is replicated thrice, and no two copies of the same block are on the same machine. Okay, and when the data node fails, the lost blocks are copied to the other nodes. Okay, so as we said, one block has got three copies. When one data node dies, there could be hundreds of scenario, power failure, this, that. One of the data node, if it dies, there are still two blocks left, and out of these two blocks, one more copy is created. Two copies is still left if one of the data node dies. If two data node dies, we still have got one copy left, right? And therefore we can again recreate two more copies in order to protect the loss in the future. Say, what if the third node also dies after 10 minutes? Therefore, HDFS quickly replicates the bring up the replication factor to 3. As a data node dies, the replication factor of that particular, all those files which were stored on this machine, the replication factor comes down, and immediately the replication factor is brought back again using the other replica of the lost blocks. Okay, so this is called replication. So HDFS is made up of one name node and many data nodes. Name node keeps the book, does the bookkeeping, that what is where kind of thing, and every file is broken down into small slices, small blocks we call them, and every block every block is replicated thrice. Every block is replicated thrice, and in case one node dies, the replication is recovered by remaining remaining copies of the blocks. All right. Now, all right. So this was replication. Now, a common question is that this user will come to the name node, and name node will gather the data from all the data nodes and give it to the user. Answer is no. This is not the way happen. It happens because in this kind of architecture, name node will become the bottleneck. Okay, if name node starts giving every file, then there is no use of such file system. It cannot support it cannot support more than few concurrent file reads. Hence, the conversation between the user and the HDFS looks like this. User comes to the name node. User, so don't get intimidated that you as the user will have to interact with blocks and then have to gather it. No, this driver, the command will do that for you. So you ask the command, say, give me this file. Command goes to name node saying, hey, can you give me this file? Name node says, you get it by yourself. Here is the address of the data nodes. Here are the data nodes. Name node replies politely saying, here are the data nodes. Take uh, these are the IP address of the data nodes, and these are the IDs of every block that you want. Now it's up to you whether you want it now, later, in parallel, in sequence. It's up to you how you want to access the file. Go to the data nodes and get it by yourself. That's what name node tells the client driver, and client driver starts talking to data directly the data nodes. Okay, this is what happens in the conversation. All right. So wow. Now let me take your questions. I know I have missed a lot of questions. Let me just take one by one. A question from Sasti is, all right, now let me just, okay. Question from Sasti is, where is the data node? Where is the data node? Is name node a server and data node? All of these are servers. Name node and data node, all of these are servers. Okay. And generally, the name node and data nodes are kept on different machine, but in our case, name node and data node both are on same machine. Okay, I'll show you. So you have HDFS here. HDFS has got name node and data nodes. Name node, let's take a look. Name node is on what machine? This machine, right? And right, 172 this. And on this same machine, these are the other services that are running. So you have name node and data node both on the same machine. Okay. So in our case, we are little miser people. So we have kept name node and data node on the same machine. Okay. All right. Next question from Sasti was also, what's the advantage of leaves less unused space? As in, it'll give you more storage space if you have smaller blocks. Okay. This diagram is better in the way. So here, if you see, if these pebbles are smaller, then they can more can fit into the jar. A question from Prem. Why replication factor is 3, not 4, not 2? Can anybody answer that? It's a tough question. Any? Okay, let me try to answer and give my reasoning to, because I too have the same, you know, right now our replication factor, if you go into Ambari and you go into say services, okay, does it show the replication factor anywhere? So total number of blocks are these many, and these many total directory files and everything. Okay, it doesn't show you anything here. Let me go into config. Here it should show you some default. Okay, not there. Let's go into advanced. Here you can see the block replication has been set as 3. Okay, if you are admin you can edit all these values. Okay, let me try to answer this question. Why replication factor is only 3, not 2? Okay, let me take a hypothetical case. What could have happened if it was 2? Okay, in normal cases we generally keep 2 copies of the data, right? One backup copy and one the running copy. Yeah, but if you look at data node closely, a data node will contain almost one block from every file. Okay, so a data node, if you look at it closely, the whole from the whole file system, it might contain one block from each. And what if we lose one block from every file? So the whole file system is is wasted, is no longer valid. Because a single file, if you lose one particular block, any particular block, the file is useless. Okay, the file is useless, file is corrupted if you lose even a single block. So losing a data node is far disastrous in our case, as opposed to our file system that we built in the beginning, that hypothetical file system which we built, where we were in case there we lose one machine, we only lose few files that were on that node. But in case of data node, the chances are that every data node will contain one block from every file. Therefore, loss of a data node is a very big disaster. Loss of a data node is a very big disaster. Therefore, it is recommended to have more than 2 copies of data node. Okay, okay. And why don't we keep 4? The reason is that 4 becomes little too high. But there are some file system where you're keeping critical data. You want to basically keep many copies. The other downside of having more replication factor is not only storage, but when the file is being created, there will be parallel too many read writes. Okay, so yes, so that's the one reasoning which I can give you behind keeping the replication factor as 2, as 3, not 2. Because 2 is the common one whenever we keep a file. But here, data node, disaster of loss of a data node is actually bigger disaster than losing a normal hard drive. Okay? A question from Sasti. Replication scenario doesn't look that much cost effective. Yes. So the cost is another one. That answers why not 4. Okay. A question from Ashwini. No two copies are on the same data node, meaning some X file will not be on the same data. Okay, and this one second part I've answered. Okay, let me try to explain it this way. So let's say we have 1 GB of a movie. Okay, it'll have how many blocks? How many blocks? Anybody? Yes. If each block size is, yes, 1 GB divided by 12, which is basically 1 GB by 8, right? So sorry, 1 GB by 128 is 8 blocks, and every 8 block will have 3 copies, so 8 into 3, which is 24 blocks, is what you will have. Okay, all right. Okay, Ila's question is, when the node that failed. Good, very good question, Ila. So the question is very interesting. So question from Ila is that when the node that failed came up back after some time, now there will be 4 replicas. Does the system delete one so that total is 3 again? Yes, it will delete. Okay, we can demo you that part. But yeah, but for that we'll have to shut down one of the data nodes. Or you could also say in the same way that earlier we had set 3 replication factor. If we reduce it to 2, what happens to extra block? Okay, the answer is delete. Abru's question is, if the default replication is 3, then the number of nodes should be greater than 3 billion. Okay, this is great. Answer is yes. Greater than or equal to. Okay, I'll show you this. So if we increase a replication factor of a particular file to beyond 5, Right now we have how many data nodes? Right now we have 5 data nodes, right? If we set the replication factor to 6, it'll give an error saying the file is, it'll accept as a command, but it'll keep on showing us, it will keep on showing us that there is something wrong. The file is under replicated. The file is under replicated. Great question. Okay, a question from Lokesh. Will name node have the same replication factor as data node? Yes, all of these. Okay, so here, so the data of name node is not replicated like this. Okay, so the data, it's a very critical question what Lokesh has asked. Question is, what is the data of name node as well replicated? Because here the name node here name node also is keeping certain data, which is basically metadata, as in data of the data, like when the file was created, how many blocks are there, what is the size of file, and so on. So question is this metadata replicated? So we will come back to that very soon. A question from Arun, sorry, a question from Ravi. Is storage still a problem here in this architecture? Say 100 TB of data spread across n number of node times 3. Okay, how is this different? Yeah. So basically the question is, so we are trying to solve those few problems here. Okay, the problems we discussed, the problems we faced was one, failover and backup. By the use of replica, this is solved. Even if you created any other file system, that will at most, if you keep backup, it'll keep like two terabyte of storage. But in our case, it's 3 terabyte, but it's far more robust. How would distribute and distributing data uniformly is very much possible because we are breaking down every file into small pieces and distribute it automatically using algorithmic techniques of balancing data is happening underneath, so human doesn't have to intervene there. Is it best value for money? Yes. The reason is you can buy smaller hard disk, say lesser than, but the hard disk has to be bigger than 128 MB. Okay, therefore the money is saved. You can buy used hard disk. If you do not know, when Google was being built, they bought old hard drives from the whole college, whole university. They bought the old hard drives and built Google using those about to be thrown away kind of hard drives. And because of this kind of architecture, they were able to use those. What about increasing accessibility? This is anyway done, and scaling out. So yes, in our architecture, yes, it consumes 3 terabyte, but it is far more robust. But the fact is that the hard drives are cheaper, just that they fail a lot. And hence, you need kind of 3 replication. A question from Ila, brilliant set of questions. Um, Thank you, Ravi. A question from Ila. When the client issues the call to name node, it will return the IPs of 3 replica. How does the client pick up the one? Okay, so generally this is a very good question. We will talk about it at a later point of time. There is something called rack awareness. Okay, so HDFS is generally aware about the distances between the computers. This has to be configured by the admin. HDFS does not discover the architecture by itself. Instead, the admin has to configure the whole network in the form of a tree. And we will come back to the rack awareness when we are discussing MapReduce. But based on the rack awareness, the client driver picks the one which is closest to it and is least busy. Okay, least busy. If a particular replica is busy, name node even keeps the record of that and will give you the nodes which are relatively free. Brilliant questions. A question from Yogesh. Can we create 2 to 4 nodes on the same machine while installing on our local? In the default config, no. Okay. Only you can keep one name node plus one data node. Reason being, if every data node and name node runs on a port, name node and data node has different ports, but all the data nodes block the same port. Therefore, running two data nodes on the same machine is possible, but it is little more tricky by changing the ports. What's the common ratio between the name nodes and data node? Name node is one and data node are many. Okay, we will the generally data nodes, we keep on adding we keep on adding data nodes as and when the data gets filled up. The general strategy is this if you look at this question, it's important question when we look at from the scalability point of view. As and when the storage gets full up to 75%, you double the capacity. Okay, you double the data node capacity. Okay, this is how the scaling happens. All right, so Kulbir's question is, it should be configurable. Yes, it's configurable. Yes. Okay. Okay. He was actually answering to the question about why it's 3, not 4, not 2. Replication factor is 3, not 4, not 2. Good. Thank you, Kulbir. Then Ila's question is, 2 is insufficient, could be more than 3. Yes. 2 is insufficient, therefore we keep 3. Okay. Good. Good. Thank you, Stanley. It can be any number. Yes. 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 So question which I was trying to answer, Stanley, was that why 3 is kept as the default? Okay, good answer. Yes, very good answer. So 3 is just the default, okay, which can be definitely changed specifically for important files, in which case the replication factor will be increased. Brilliant answer. So this is how generally we do things here. In case of even our cluster, some of the data is really huge, and we know that we also have a copy on our local machines. So we have just kept the replication factor of that particular data as 2. Great. A question from Ella is, want the replication factor picked up depending on the intensity of usage? No. So this is called auto replication. Okay. Okay, so what Eli is suggesting is that want the replication factor picked up based on the intensity of usage of data. This is something very interesting. This is called auto scale, auto replication. And there are companies built around just this idea. For example, a company called Qbol provides a modified HDFS, and one of their senior engineers was actually giving morning sessions of my classes, Swati. So basically, they built an auto replication HDFS. Okay, so as the load grows, there is a movie that's being watched by many people. So accordingly, their system notices it and start increasing the replication factor. So yes, but in the default settings of HDFS, that's not a part of it. Okay. A question from Ashwin. If there are more than 4 to 5 nodes, what should be the replication factor? So again, I would still recommend 3. Okay, because if you start increasing replication factor, keep in mind that the whole file is being replicated. Therefore, it might start becoming little too much of, uh, you know, uh, disk intensive. Prem's question is, but with replication factor of 2, the data will not have the copy of the complete file system. Okay, yes. If replication factor is 2, then we'll have only 2 copies. And the risk of losing data node will is actually a disaster. So I'll give you one good example. In the last sessions, what I used to do is I used to have 2 people in the session, and both of us used to record the same session, and that too got corrupted multiple times. Okay, so yes, just to defend against the unforeseen situations, we keep 2. We keep the replication factor at more than 2. Okay, the other reasoning I can possibly think about is there are 2 kinds of disasters. One disaster is rack level disaster, as in what is a rack? Rack means multiple computers are stacked in an almirah, and that almirah is kept in data center. So there is a rack, and each rack is being kept in the data center. So first disaster could happen is at the rack level. So all the computers in the same rack will get lost. Okay, will be burnt, will be inaccessible, will be out of this. So all the data nodes in the same rack will be inaccessible. So in case those 2 copies are in the same rack, okay, therefore we lose all of that data. Okay, the other disaster, so basically that's why we have 3 copies. Okay, so first disaster is on a computer level, that a computer is down, and second disaster is on the rack level, and third disaster possibly could happen on the data center level. Okay, but data center level is little too much, therefore it's too rare. Okay, so those are the reasons why we keep the replication factor as 3. Okay, so question from Prem is, you'll have only 2 copies of 128 MB file, all of the blocks. Okay, we set not on the block level, we set the on the file level. Okay, there are a few more questions. So yeah, a question from Ashwin. When the client asks for a file, there are many replications of a file to which the name node will point. Okay, so the name node will generally hand over the list of all the files or all the blocks of a file, and will let the client choose the one it likes. Okay, Okay. So, a point from Stanley while answering Lokesh's question: metadata is not replicated because it's not stored on HDFS. That's right, because it's a part of building HDFS. It is stored on the local file system, but metadata has to be backed up. Yes, we will consider it in the next session. Uh, we will in the upcoming talk. Okay, yes, I missed to talk about Zookeeper. Thank you, Sasti, to remind me that. All right, I hope I don't forget it again. I'm noting it down here. Okay, okay. So Amrutayan's question is: when the data is being injected to the data node, does the of replication to other two nodes start after it completes the copy of data or first? So it happens in parallel. I'll talk about it in a minute. Okay. Okay, so Aswin, I can take Cassandra's question later in another session, probably. Yes. Next question is: what if name node is inaccessible? We will take it again after a while. Okay, and a question from Ila: what determines which data node should be on the same rack? Is this yes? Let me just take it a bit later because that's something. It's a part of plan. Okay. A question from Amrita, and let me explain. This one is a very good question. Question is: what if the data node goes down before the replication has started? Okay, okay. In this particular case, okay, so let's say a file has been just created, and the node on which it was created was about to do the replication, and it has gone down. In that cases, yes, we lose the data. It will say that your file system is corrupted, one of the file is not accessible. In these cases, in these corner cases, you will have to manually go to the file system and then delete that particular file from the metadata. Because for this file, metadata exists, but none of the blocks exist. It'll keep on saying under replicated file or corrupted file system. Okay, in these cases the file system does get corrupted. Okay, Prem's question is how the health of data node is detected by name node before giving the address of data node to the command. Okay, so basically the name node listens to the heartbeat being sent by data node. If data nodes do not send heartbeat for some time, they are considered as disconnected. All right. So if basically it's the duty of data node to keep sending the information to name node, because name node is a precious resource. Name node wants to stay relaxed. Therefore, each data node is supposed to inform name node saying that hey, I'm up, and name node keeps timing out each data node in case they do not respond or ping frequently. All right. So heartbeat is something internal to the HDFS. All right. Now let's move to okay. So Zookeeper is something still pending. So let me take up Zookeeper because that's not. I think it'll be better when we talk about Zookeeper after a while, because we are coming to a point, a topic which would include Zookeeper. Okay, this is actually nice. All right, now let's great, great. So it's an overview of the architecture again. So this is a client. He wants to read data, and there is one client who wants to write data. Okay, this client wants to read data, and this client is writing data. And so the way it happens is the client who wants to read data goes to name nodes, gets the metadata, and metadata is name of the file, number of replicas, date, and etc., is given back to the client, and then client start talking to individual data nodes. Okay, so these are the data nodes. Like there are five computers here, three computers on one rack and two computers on another rack. Okay, and so this client is reading, this client is writing data. Okay, so this client is writing one block here, second block here, and this block is going to get replicated like this amongst the data nodes. So as the client starts writing the blocks parallelly, it starts copying to the neighbors. Okay, so basically the client writes the fresh copies, and the machine, the data nodes, replicates by itself. Okay, replicates by itself. So client writes to one of the nodes, and that node starts replicating. Okay, the same thing has been demonstrated here as well. The HDFS client comes in, talks to the distributed file system. This client wants to create a file, so it goes to the HDFS. As in the HDFS, this client basically gets taken to, this client is being taken to the name node. Name node makes a temporary entry saying that okay, fine, I have made an entry, but this is temporary. Unless you confirm me that the data has been written to data node, I will not commit this file. I will not consider this particular write. In case you don't come back and confirm to me that data has been written, I'll delete this entry which I'm just making. So a temporary entry is created at name node metadata, and then the client goes to individual data node, writes the data there, and that individual data node confirms to the name node, yes, that particular file has been successfully written. And then name nodes commits the metadata changes. Okay, and parallelly the data node starts replicating the block to other machines. Okay, again, again, let me recap what does it mean by rack. Rack is like a big almirah. The only difference is in this almirah there is a router associated with each almirah. And what is a router? Router or hub, you can say. Router makes it possible that all these computers which are kept in the same. So okay, let me explain again. So in the rack there is a power board and there is a network cable slot. Okay, and every almirah, every rack has got a hub or a router. We generally keep it a hub so that all these computers which are kept on the same rack become kind of connected to each other in a very fast manner. So the two computers sitting on the same rack are neighbors, and they can communicate with each other faster as compared to two computers sitting on different rack. This computer here, this computer here, and this computer here are farther from each other as compared to these two computers. These computers are closer because they are on the same rack and they're connected to the same hub. Therefore, the data transport between them is going to be faster than data transfer between this and this. Okay, but at the same time, the loss of the rack is quite a probable thing because a rack is connected to the data center through a single wire. In case that wire gets some problem, this rack will become out of the network, and therefore it's important to keep the third copy somewhere. So the general thumb rule, okay, this something is not mentioned here, but yeah, the general thumb rule of keeping the three copies. We talked about replication factor as three. First copy is on one computer, second copy is on the same rack but on a different computer, third copy is off the rack. Okay, so there are three copies of the same block. One computer containing the first block. The second block would go to the neighbor of that computer. Why so? Because in case one particular computer. So let me try to draw it. I think it'll be better because this is a very important topic. And these strategies have changed a couple of times. All right, this is asking me to discard and I can't discard. Okay, let me just try to see if I can. Just give me a second. I'm trying to. All right, so I think it'll happen now. Yeah. Okay, so here we go. So let's say first copy is here. Okay, and or let me just try to say first copy is here, second copy is so second copy will be here, and third copy will be here. Okay, so you can think of it as this being copied here and yeah. Okay, so sorry, yeah. So let's say first copy is here, second copy would be here, and third copy will be here because this is rack 1 and this is rack 2. Okay, so when a reader comes, when somebody wants to read the data and it fails to read from here, let it fails to read from here, it can quickly go to the next node which is nearby and start reading from there instead of going to somebody which is very far. All right, therefore 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 Two copies are kept close by, and third copy is kept far away. Far away as in, because in case there is a disaster, in case there is the fire happens at this node, okay, the fire happens at this node, at least a copy is safe here. That's why the architecture tries to keep the data far as well as close. All right. This is probably one of the reasons why we keep the data that way. So two copy on the two, one copy on one computer, second copy on the same rack, and third copy on different rack. A question from Ila: does HDFS know that the third copy should be kept on separate rack? Yes. So by default, these are called replication strategies. Okay, there are many replication strategy, and the one I have talked about is one of the strategies. If if you are implementing your own strategies, HDFS allows you to do that. You can extend the replication strategies and can configure while while installing HDFS. Okay, do I make sense, Ila? So the strategy I talked about is part of the HDFS default behavior. All right. Now let's move ahead. So we talked about the anatomy of the file read. Anatomy of the file write is what we have talked about, and the anatomy of file read is very similar. Okay, there is HDFS client, it goes to the distributed file system, goes to the name node, and then it gives the block locations, and then it goes either parallelly to read the data node, or it goes in the sequence. All right. Yes, Prem, you have a question, you have raised the hand. All right, now let's talk about one question which all of us are talking so far. Okay, everybody wants to know that part. Okay, a question from Ashwin is: client will contact HDFS first and then name node. Basically, when we say HDFS, it's basically local driver. Okay, it's a driver. The way you have ls command, ps command, and all these commands, or you have like jdbc driver. In the same way, when I say HDFS here, we are actually, this is basically, we are talking about kind of you can say that it's a part of the client driver code. Okay, it's a part of the client driver code. All right, do it make sense to you? All right, now the important question which some of you have already asked is, question is name node single point of failure? The answer is no. There are many strategies, and the most rudimentary one is keeping the backup of namespace image and edit logs. So what are these things? Name node, as we talked earlier, keeps the data in two form. Okay, one in the memory and other in the disk. In the memory, the whole metadata is an updated one. Okay, but it can't keep writing the whole memory again and again to the disk. So what it does is it periodically makes the snapshot of the metadata from the memory into the disk, and then keep on making edit logs. Okay, it's like the accounting, if you are aware about how does accounting work. So how basically, okay, so what, let's say this is your memory. Okay, this is the memory, and it is, we have written something here. Up to here it's written. This is, let's say, RAM. Okay, and this is, let's say, disk. Okay, so initially, okay, so this is not RAM, let's call it disk. Disk, and this is a kind of image, we call it image, and then we have something called logs. Okay, these are logs. I'm really bad at handwriting, so excuse me for that. So these are logs. Okay, and this tool does, so let's say there were, we keeping the metadata, this is metadata, and periodically it creates image of the RAM, because it's quite intensive process. Now we have find the metadata has been kept in the disk. This is one file, this is another file. Now as and when the change happen here, same change will be added here. Okay, something more got written on this. Okay, something more got written here. So instead of writing through the image, it will keep on putting it into the edit logs, just like Oracle's transaction log. Once after a while, it will create the complete image of the RAM again. Okay, like this. Okay, so it will not keep updating the image continuously, because what happens is, if you try to mirror the RAM again and again onto the disk, the whole process becomes too much time consuming. Okay, because writing to the disk is a very big deal. Second, if we do not keep the copies, if we do not keep something in the disk, if the computer turns off, this memory, this thing is transient. If the computer get turned off, this goes away. This goes away. Therefore, this, therefore we have image and the log. Okay, so basically, name node keeps data in the disk. Name node keeps a copy of metadata in the disk in the form of image and edit logs. Okay, just like an account as well as the journal. Okay, these edit logs are also called kind of journals. Now we could keep backing up this file system to another place, and name node allows us to do that. If we keep copying the location where this image and the edit logs are kept to some other machines, that's first way of avoiding the single point of failure. But okay, but in case it fails, in case it fails, what happens is, in case this particular machine failed, okay, so recovering data from network, okay, creating the metadata from the image and the edit log is manual, and that's bad. So this is generally called secondary name node. Okay, in the secondary name node, the process is very similar to what we have described here. We basically keep two copies of image and the edit logs. In case our name node dies, we recover the image from image plus edit logs. Now this is called secondary name node, secondary name node architecture, where we keep a secondary copy of the name node in the disk, and we have to bring it back manually. Okay, in case name node dies. A question from Ila is, so there is a window of failure if name node goes down? Kind of, yes. Okay. If the edit logs are not updated and the name node goes down, in that case, yes, there is a window where we could suffer a loss of a file. Now the next, the third kind of a architecture, which actually is quite standard, where we keep something called name node and standby. This architecture was introduced. This was introduced as part of Hadoop 2.0. Okay, and how does it work? There is always a mirror of name node, which is kind of a twin of name node, but it's in a silent mode. Nobody, I mean, no, the client don't talk to standby. Client talk to the name node. Okay, so I think this architecture will take a little bit more time, and let's do it over tomorrow. All right, we'll go into the details of this one. Don't worry about the time and all. Okay, everything is going great. So I really like the question in the session, and we'll meet tomorrow and we will continue from this architecture. Okay, all right. Tomorrow we are meeting tomorrow, Lee. Same time, 3 hours before this time. Right now for me it says 11 p.m. IST. Okay, so for me it'll be 8 p.m. IST. We'll start tomorrow. So I mean the same time which we started today, 3 hours before this time. All right. Okay. All right. Great set of questions, and I look forward to have the session tomorrow. I hope I have not skipped anybody's question. If I have, just feel free to drop me an email. I will try to answer, or drop on the Facebook students page. Okay. All right. See you tomorrow. Bye bye. Yes, these slides are updated here. Ashwin, are you able to log in? Can you click on this presentation open, and it should be there. The slides, all the slides are shared with all the students, so you can look at the presentation here. Okay. Bye bye. Have a good day. Bye, Sasti. Bye, Ashwin. Bye, Abru. Bye, Lee. Bye, Ravi. Bye, Ron. Bye, Ella. Bye, Stanley. Bye, Prem. Bye, Lokesh. Bye, Margani. Have a good day.